All right, welcome to guide sheet number 2 on waves. We're looking at specifically to start with your boundary behavior. What happens when a wave reaches a boundary between two different media? That's objective 4.5.1 on your objective sheet for waves and simple harmonic motion. The background reading is here for what happens in boundaries. We're talking about pulses mostly right here as opposed to wave trains. The basic rule for what's going to happen between a free and a fixed end, in either case, when the wave pulse reaches the boundary, there's going to be some kind of reflection bouncing back in sound we call it an echo of the wave energy. The difference is if the end is free, then the reflected pulse is going to be the same orientation. Meaning if it started up, it's going to come back up. If the end is fixed, like it's tied to a rigid barrier, then when it hits off that fixed object, the motion is going to cause the wave to actually invert. So the reflected pulse that comes back at you will be inverted, upside down. Okay, so here's the waves on a string simulation again. We'll start a pulse heading down toward the end over here. Now this end is fixed, so this little green dot here is tied down. It can't really move. So what happens is that the pulse, which was on the upper section, is now on the lower section. If we make that end loose so that that last green molecule can actually move up and down and start a pulse down the string, because that green molecule can move, it's going to allow it to go up, and we get the reflected pulse bouncing back, going in the opposite direction, a 180-degree change in the velocity, but it comes back on the same side. So that's the same. Those are the two basic rules, things to look out for. So in number 2, if the incident pulse, and incident simply means going in to the boundary, and here's the boundary right here, then it's going to, if that end is fixed, as it is here, then the reflected pulse is going to be inverted, flipped upside down. If that end is free, then when it comes back, it's going to be the same. Now, it'll also typically, since some of the energy will be lost or go into other things, typically the reflected wave or pulse will tend to be smaller than the incident wave in terms of mechanical waves. Okay, now we'll look at what happens when a wave transfers between two different media, two different things. So in this one, we're going to go from a more dense media, like water, to a less dense media, like air. Now, what happens is the heavier molecules cause the wave to move slower in the water than they do in the air. So they're going to move faster over here and slower over here. Now, because of other things we've learned about waves, it's going to have a couple of impacts. First of all, the reflected wave in medium 1, the one that comes back, will not be inverted. It's like hitting a fixed end whenever you go from a more dense to a less dense media. Now, if you do have if we're going the opposite way, from less dense to more dense, then we could have an inversion. But the reflected media will not be inverted because it's similar to hitting a free end whenever you go from more dense, heavier materials to less dense. Now, the speed of the transmitted pulse, the one that goes through into this lighter medium again, will be faster. So the speed will be greater than it was before. So it will speed up. The reflected pulse, on the other hand, will still be in the same media, so it's going to be moving in the same speed. The speed of a mechanical wave is dependent on the stuff it's moving through, as we saw in guide sheet 1. The wavelength of the transmitted pulse. Now, we have the velocity has gone up, and the frequency of the wave itself hasn't changed. But since velocity is frequency times wavelength, if we want the velocity to go up for the same frequency, then that indicates that we're going to have the wavelength also go up. So the wavelength is going to be greater in the transmitted pulse. So if I tried to draw this transmitted pulse, it might look something like, it's not the amplitude is different, but the wavelength is going to be longer. Okay, so it's going to be a little broader across than the original wave. This can also cause changes in direction, which we'll talk about with refraction. So different media cause the mechanical wave to move at different rates. Okay, now in this one, wave pulse is moving from less dense to more dense media. So essentially the reverse of what we just had. So what happens, we're just going to essentially end up with the reverse of the information we had before. Again, here we're going to be faster in the lighter media and then slower. So when you're hitting the more dense material, that's more like having an end that's fixed. So the reflected pulse will be inverted because it's more like hitting a fixed end. The heavier material is more rigid, more difficult to move. The speed of the transmitted pulse will be actually slower than, less than the speed of the incident pulse. The reflected pulse, again, it's going to be in the same material, so that's going to be the same as. Now, again, from the wave equation, velocity equals frequency times wavelength. We're expecting the velocity in the transmitted pulse to go down, so for the same frequency wave, that indicates that the wavelength must become less. So if we were to look at this one, the transmitted pulse, now the transmitted pulse will not be inverted, but it will be shorter in wavelength. So this distance is less than this distance. Okay, so to summarize, when a wave passes across the boundary from one medium to another, the speed is going to be greatest in the least dense material, so it's easier to go through materials that are less dense. Since the frequency is the same and the speed is greater, the wavelength must be greatest in the least dense material. Now, if we reverse those questions and ask what the speed is, would be smallest in the more dense material, and the wavelength would be shorter in the more dense media. And then the reflected pulse would become inverted only when the wave is moving from the lighter stuff to the heavier stuff, when it's more like a fixed end, so less dense to more dense. Alright, so we're going to draw a couple of reflected and transmitted pulses here for a couple of situations to see if we got this figured out. Okay, so we're going to start from the more dense material to the less dense, so from slower to faster. Now, whenever it hits a more dense to a less dense, it's like having a fixed end here, having a moving free end here, not fixed. And therefore, when it comes back, it's going to come back in essentially the same orientation and the same wavelength. Now, when the transmitted wave is going to continue through in the same orientation, but it's going to be going faster, so that wavelength is going to end up being longer. So this wavelength is a bit more than this wavelength. Now, if we do the reverse, we're going to go from the less dense media toward the more dense media. And here's our boundary. This boundary is going to behave more like a fixed end medium. It's going to be hard for the lighter material to move the dense material, so it's going to act more like a. Okay, so therefore this is going to behave more like a fixed end. That makes the transmission, the wave that comes back, the reflected wave, is going to be the same wavelength. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And but inverted upside down, so it's going to look something like that. Now the wavelength, the transmitted wave, is going to be in the same orientation, but it's going to be going slower, so it's going to have a shorter wavelength. So let's say 1, 2, 3, 4. Alright, so that gives me 2 points to work with, and something like that. So shorter wavelength, moving slower, but still moving in the same orientation. The reflected wave, anytime you're hitting off a fixed end, hitting off a more dense material, it's going to come back inverted. Okay, so that's the basics of how waves interact with boundaries between two different media, and the types of reflections and transmissions we get.